In the first few lectures, we discussed the definition of an embedded manifold and an abstract manifold. Now we want to explore the infinitesimal structure of a differentiable manifold, and in particular, we want to extend the definition of the derivative or the differential of a map between Euclidean spaces to our more general setting. In order to do so, we need to define the tangent space of manifold at a point, and we need even more. We need to give a structure of differentiable manifold to the union of the tangent spaces to the manifold at any of its points. That then, the union of those tangent spaces at any point is going to be called the tangent space of M, and we are going to see that it is indeed a manifold whose dimension is double the dimension of the manifold M. So we are going to introduce all these concepts in order to see that the differential of a map is well defined and that it satisfies analogous properties as the ones we have in the Euclidean case. So first, we're going to focus for a second in the Euclidean case. We consider a map between an open subset of R to the M to R to the N, okay? Now let's assume that this map is differentiable, okay? We're not going to discuss the concept of differentiability of a map. Let's assume that that's well known. The derivative or differential of f at a point x is the linear map, okay? That is the best linear approximation for f at the point x. And the matrix of such a map in the canonical basis of these two Euclidean spaces, R to the n and R to the n, is just the Jacobian matrix. Okay, it's a matrix that it is n times m, okay, and whose entries are just the partial derivatives of the components of f with respect to the variables. It's just that. So we know this is a very well-known definition. Something that it is interesting even in this Euclidean case is that if f is a CR map, what happens when we have a CR map? We are going to consider we are going to consider partial derivatives of the components here of f with respect to our variables. And of course, the sum of the k's has to be smaller or equal than r. What we ask is that all these partial derivatives are actually exist and they are continuous. But what you can see is that when we consider the differential, okay, for instance, from the matrix point of view, here we have that the entries of the matrix are themselves already derivatives. And so we cannot ensure anymore that we can derive them r times, because that would imply deriving the initial components of f at least r plus 1 times. What we can ensure is that we can derive all these entries r minus 1 times and that the derivatives are going to be continuous. And as a consequence of this remark, we have that this map over here, built by using defining the differential of f in the point xy as the differential of f at the point X applied to Y is a CR-1 map. Okay? So we are losing a degree of differentiability when we consider the differential of a map. If the map is CR, the differential is just going to be CR-1. Okay, a very fundamental result is that the chain rule holds. If we have a map between U, which is an open subset of R to the N, or R to the M, and R to the N, and G, which is a map between an open subset of R to the N and R to the P. And besides that, we have that the image of F is contained in the domain of definition of G, then we can consider the composition. And if these two maps are CR, the composition is also CR. But the situation is even better. We can actually calculate the differential of the composition at a point X and relate this differential of the composition at X with the differentials of F at X and of G at F of X. And what we have is the chain rule. The differential of F composed with G at X is the composition of the differential of F at X and the differential of G at F of X. Okay, the differential of F at the point X is a linear map between R to the M and R to the N. The differential of G at the point F of X is also a linear map, but now the domain of the linear map is R to the N, and the target space is R to the P. And the composition is a linear map between R to the M and R to the P. Exactly as it happens for the differential of the composition of F and G at X. This is also a linear map from R to the M to R to the P. So, and of course, that does not imply that we have the chain rule, but at least we don't have problem with the domain of these maps and the target spaces, and indeed we don't have a problem with anything. This is very well known, and besides that, if there is the natural interpretation when we consider the matrices of these maps in the canonical basis, and it's that the Jacobian matrix of the composition of F and G at the point X is going to be the product of the Jacobian matrix of F at X and the Jacobian matrix of G at the point F of X. So we have the chain rule for differentiable maps defined in Euclidean spaces. What we want in order to extend this kind of object to our abstract setting is, first of all, defining the tangent space at a point for the abstract setting. And that's actually not completely obvious how to do it. How do we do it in the embedded case? In the embedded case, we have a submanifold of an Euclidean space, M, and we consider a point of this manifold M. Now we fix a parametrization phi of a neighborhood of X in our manifold M. And let us remind ourselves that U is an open set of R to the n to the small n, where small n is the dimension of our manifold. Since it's a parametrization, in particular, it's injective, and so there is a unique parameter c that corresponds to the point x. And we can define the image of the differential of phi at the point c. Since this map over here is a linear map between r to the small n to r to the big N, this image is going to be a linear subspace of r to the big N. So we obtain in this way a linear subspace. Sure. So this is very nice because we can define the tangent space, the best linear approximation to our manifold at a point x, just as the image of the differential of the parametrization, and it has a natural structure of a vector space. But there is a small problem, of course, that it's not difficult to fix, and it's that a priori we could think that this definition depends on the parametrization. It is not 100% obvious that if we consider another parametrization, the image of the differential is going to be the same, right? And let's go into discuss this point soon. Here, what we have is a picture of how the situation works. Here we have U, which is in a darker color, the domain of definition of our parametrization, and the image of the parametrization. And the space that is pictured over here is not the tangent space, but x plus the tangent space. Okay, here we consider the points that are the form x plus y, where y is an element of the tangent space of M at the point x. And why do we do that? Because in general, the tangent space, if you're in the embedded situation, is a linear subspace. That is true, but it's a linear subspace that does not contain the point x. And visually, it can be weird to think that the best approximation, best linear approximation to our manifold at the point x does not even go through the point x. In order to make this space to go through x, we have to consider the points of this form. But why are not considering that as the definition of the tangent space? Because you win something, and it's that your new definition fits better with the idea of best linear approximation, but you lose something, which is that it's not a linear subspace anymore, at least in general. In general, this is an affine subspace of R to the big N, but in general, it's not linear. If X does not belong to this space, this is not a linear subspace. And so, in order to keep the structure of vector space, we are going to prefer to consider the tangent space of M at X instead of this set. All right? Okay. There was something missing in our discussion, and it's the fact that this definition of tangent space does not depend on the local chart. We're going to review what happens. So we have two parametrizations, of neighborhoods of X in the manifold M. And we consider the parameters that correspond to X for both parameterizations. We have Y, which is the parameter that corresponds to X for the parameterization phi, and C, which is the parameter that corresponds to X for the parameterization psi, right? And we defined the tangent space in two different ways. We defined the tangent space of M at the point X as the image of the map differential of phi at the point epsilon, y, and as the image of the differential of psi at the point C. And we have to check out that these two linear subspaces are the same one. Otherwise, our definition is not a good one. It depends on local charts, and so it could be useless. It couldn't be intrinsic. So we need to see that it does not depend on the choice of local charts. What we can do? We have here the two parameterizations, phi here and psi, and the way to go from one of these parameterizations to the other is by using here this map, which is just the map of change of parameters. And this map, we know that it is, if the manifold is CR, it's a CR diffeomorphism, right? It's a CR diffeomorphism between open subsets of R to the small n. So since everything here it's in Euclidean spaces, we can apply the chain rule and we obtain this expression, right? We calculate the differential of psi at the point C. It's going to be the differential of the change of parameter map at the point C composed with the differential of phi at the point Y. Y is just the image of C by C composed with phi minus 1, right? Because C of C is X, phi minus 1 applied to X is Y, okay? So we have this by the chain rule, but we have more. We know that this is the differential of the change of parameter map, and that change of parameter map is always a CR diffeomorphism. So this is a linear isomorphism between R to the small n and itself. And so, okay, this is what I was just saying, is a linear isomorphism of R to the small n, and in particular, the image of these two maps coincides. So our definition does not depend on the choice of parameterizations. And the tangent space of the manifold at the point X is well defined. Let us introduce an alternative description for the tangent space at a point. We can identify the tangent space of manifold at a given point with a set of equivalence classes of curves. If we consider, for instance, a curve as in here, defined in a neighborhood of 0 in the line, and whose image is in N, a curve such that it associates to 0 the point X, and we consider a curve of the same kind, eta, we identify them if the speeds at 0 are the same. So basically the equivalence relation is having the same speed at the point 0. And in this way, we are identifying curves with their speed vectors. And these speed vectors are the vectors in the tangent space. So it's an neural identification. How is this related to the tangent space of M at X? And more precisely, to the parametrizations, to the description that we already gave of the tangent space as the image of a differential. Okay, what happens is that if we consider a parametrization of an open subset U, of U being a neighborhood of a point X, and we consider the parameter Y that is sent to X, we can consider, for instance, all the tangent vectors are of this kind. You consider B a vector in R to the power R to the dimension of M, okay? And you consider the image by the differential of phi at the point Y. So all the tangent vectors are of this kind. And how are these vectors obtained as equivalence classes of curves? It's quite simple. You consider the curve defined this way. You fix B, which is going to be a vector in an Euclidean space, in fact, R to the dimension of M, and this curve over here. This is actually a map from a neighborhood of the origin in the line to M. And the image obtained at t equals 0 is the point X. And if you calculate the speed, if you calculate the derivative of this at 0, as we are doing, what you get is exactly this vector. So a curve whose equivalent class corresponds to this vector is this one. And we can try to use this idea in the abstract case. In the abstract case, there is no neural embedding in a manifold. So yeah, using parametrizations in the way it was defined here, it's not going to be possible. The tangent space has to be defined in a different way. But for instance, it's possible to define this equivalence class of curves. And that's going to be a way in which we can convince ourselves that the tangent space of a manifold, even an abstract manifold at a point, is well defined. Okay, let's try to develop this idea. Now we consider two differentiable curves, two maps from minus epsilon epsilon to M, such that the value at 0 is equal to X. And we say that they're equivalent if the differential of gamma and eta at 0 is the same. This makes no sense at all, okay, because we didn't define so far what is the differential of a differentiable map. So it is in red because it's dangerous. We are actually trying to use things that we don't know yet. So this is a problem, but we can try to define it. We can try to use local charts in order to define it. Okay, let's go. So what do we mean by the differential of gamma and eta being the same at 0? Consider phi and psi local charts defined in the neighborhood of X. Since we can actually define these concepts in Euclidean spaces, using local charts is natural. And we say that by definition that the differential of gamma and eta at 0 are the same if the differential of gamma composed with phi and eta composed with phi coincide at 0. This is a definition, okay? There is no problem now because gamma composed with phi is a map between an interval and an Euclidean space. So we don't have to worry about anything, except one little detail, that our definition depends so far because let's see that it doesn't, but so far it depends on the choice of local charts, and that's bad. If we cannot remove local charts from the definition, we cannot prove that the definition is intrinsic and that does not depend on the choice of local charts, then it's useless. Okay, so does it depend on the choice of the local chart? And the answer is no, it doesn't. And let's see why is that. When we consider gamma composed with psi and gamma composed with phi, these two maps are related by the map here, which is the coordinate change. We have that gamma composed with psi is gamma composed with phi composed with the coordinate change. And now all this map over here and this one are maps between Euclidean spaces. So we can apply the change rule, and we apply it at 0. And we get that the differential of gamma composed with psi at 0, it's going to be the differential of gamma composed with phi at 0, composed with the differential of the coordinate change at this point, 5x. And analogously, we get a similar formula that relates the differential of eta composed with psi at 0 and eta composed with phi. And what relates these differentials calculated by using psi and the differentials calculated by using phi is this map over here, which is the same in both cases. And it's just the differential of the coordinate change, which is a linear isomorphism. And that actually implies that the definition does not depend at all on the choice of local charts. If we have that these differentials to the right are the same, then it's obvious that the differentials at the left-hand side are also the same. But it works also the other way around because this map over here is an isomorphism, so we can actually compose with its inverse and make the exact same argument. So this definition does not depend on local charts, and so we can define a set of equivalent classes of curves in which two curves are equivalent if the speeds at which they travel when they go through 0 are the same. So that implies somehow that the tangent space has to be well defined. Because if these equivalence classes actually are well defined, the tangent space has to be well defined. But the problem of this definition is that it is not clear at all what the structure of this tangent space is. It's not clear at all with this point of view that it is a vector space. But it is interesting to notice that this point of view allows to understand that this tangent space has to exist. And now we maybe can use another point of view that is going to provide not just the existence, but some of the properties that it not really has. What we did over here, basically, we are going to see this later on, is it's at the end of the day, something is that we wanted to give a meaning to that. And this differential is going to be well defined. The differential of a differentiable map between differentiable manifolds is going to be well defined. We just actually did this a little bit early in order to define tangent space. But later on, we're going to see that this fits with a wider framework, okay? The framework of the differentiable of a differentiable map. Yes. In the beginning of our lecture, we reviewed the definition of the derivative of map between open subsets of Euclidean spaces. And indeed, we also reviewed the chain rule. What we want is generalizing this setting to the case of differentiable maps between differentiable manifolds. But one thing that we have to point out is that derivative is a linear map and it's obviously defined between linear spaces. In our case, it's not clear how to define for an abstract manifold a linear structure at every of its points. And that's what we tried to do during this lecture. We actually presented the situation of the embedded case, and we are using this as a motivation in order to define the tangent space of a manifold at a point. By the end of the lecture, we showed that one of the possible interpretations of the tangent space as an equivalence class of curves through a point can be generalized to the abstract setting, which actually makes clear that it is possible to make a definition of tangent space at a point, even in the abstract case. But with that definition, it is not completely clear why it is a vector space. And that's something that we are going to deal with in the next lecture. We're also going to see that the union of these tangent spaces of the manifold at any of its points is a manifold, or if you want, is a set, and we can actually give to this set a structure of differentiable manifold. Thank you for your attention.